Morning, everyone. So in this lesson, we're just going to have a quick look back at the free energy concepts that we looked at last year in relation to the equilibrium stuff that we've been dealing with here. So just a small section on free energy and equilibrium. We'll also make some connections with kinetics as well. If you remember back from last year, we had the expression the delta G is actually delta H minus T delta S. Let me just define these terms for you again here. The delta G is the change in Gibbs free energy. Why do we refer to it as free energy to begin with? Free energy, this is actually telling us the amount of energy available for work. Right. This is energy that can be used. Let's think about a battery as an example. The battery is supposed to provide me electrical energy. That's the energy that's available. This free energy concept was actually a combination between two things. We saw these as the two factors to predict whether a reaction occurs or not. The first factor here was a change in enthalpy. Enthalpy was a measure of sort of the heat content in the system. This was where we got endo and exo. And essentially, if enthalpy has way, we would prefer, we want to point towards the heat term because minimum energy is more stable. Right? So that actually preferences the exothermic direction. Well, the products of an exothermic reaction are actually more stable, so go that direction. We saw that the other feature of spontaneity was this entropy concept. Entropy, in the background, it does have something to do with energy as well, but let's represent entropy here. Entropy is actually a measure of the chaos in the system. Right? So entropy is the amount of disorder or the amount of randomness in the system. We had the second law of thermodynamics basically say systems or nature, systems tend towards maximum entropy. Right? And it was sort of the interplay between these two features here. The enthalpy here was supposed to give me, this is all the energy available, but some of this energy was actually locked away into the randomness, into the different microstates that your system can actually be set up with, right? So what we actually did is we actually started plotting. We plot a graph here. Let's just plot free energy against the reaction axis. Remember, for the reaction axis, what we have is we have reactants on the left side and products on the right side. This is plotting just free energy, not change in free energy. So let's start off with, we knew that delta G less than 0, that meant a spontaneous reaction. That means the forward reaction happens. So that means we actually start out somewhere high, and we actually, by the time we get to products, we end up somewhere lower than it, right? Now, just a quick technical note here. For some reason, we define charges at infinity. Their potential energy at that point will be 0. As long as charges are at sort of everyday distances here, those energies are actually numerically going to be negative. So if I set my 0 as sort of the extreme, my free energy might start from, let's say, negative 10. It might fall to, I don't know, negative 50, right? So yes, there is a weird sort of convention. Why do we have to have energies as negatives? But all I really care is sort of which one is closer to the 0. In this case here, the negative 10 actually marks I have more free energy than the negative 50 case. So even though it's weird with the negative, this one here still is a change, right? So change is final minus initial. This case here, the delta G here is negative. The delta G currently, as I've listed for you, is actually a negative 40 kilojoules per mole. And what we saw from chapter 5 was, well, if free energy here is actually negative, that means the reaction is spontaneous. That means the forward reaction goes. In fact, what ends up happening, we start off here, this is just pure reactants, right? All of it is just reactants. At the end of the day, this is just pure products. Because the energy diagram looks like this here, when we settle into equilibrium, when we end up hitting this sort of mixture, mixtures always have the lowest free energy. Mixtures, it's always easy to make more of a mess when you have multiple different chemicals. Mixtures have, this one here has the lower free energy than just your pure reactants or pure products. It's just because this delta G here is so large, we end up having the equilibrium lie pretty close to the 100% case. So pretty much we just say, yeah, 100%, maybe 99.99%, okay? But pretty much pushed over to that side here. What's going to happen over time is as this battery here starts using up its electrical energy here, we start using up the reactants, we're going to actually lose some of our free energy. So we're going to end up a little bit lower here. As I pick up some more products, we're going to end up ending up, that value is going to come upwards as well. We're going to hit a point where the delta G is actually going to be 0. More on this in a later chapter. But when the delta G actually hits 0, we essentially have a dead battery. There is now no more free energy that's available for you to use. In this case here, the curve actually sort of pushes over a little bit here. We still are going to spontaneously head towards a point where the free energy is the lowest, but you see that this lowest point here is nowhere near the products. I need the forward reaction to actually generate the electrical energy. If I don't have a spontaneous reaction going forwards, I don't actually have this energy available for use. All right? So that's the free energy concept here. I'm just going to give you the connection between free energy and the equilibrium constant that we've been doing. And that's actually an equation in your data booklet. The delta G can be written as a negative RT ln natural logarithm of Kc. Right? Let me just define for you some of these terms here. This delta G we were just rehashed. So this is the change in Gibbs free energy. The R here is the universal gas constant, so the 8.31 joule per Kelvin mole. The temperature here has to be the absolute temperature, so temperature as measured with Kelvin. And what I want to emphasize here is actually just this negative symbol here, right? It just basically says here, well, the R is positive, the absolute temperature is positive, this logarithm of a positive number will also be positive, and now we're just going to change the sign. So earlier when we had been saying, well, for a spontaneous reaction, the delta G is supposed to be a negative reading. It's already negative because of this negative here. The reaction will become more spontaneous, in fact, as we get a larger and larger K. So if, for example, if I want a big negative delta G, right, a very spontaneous reaction, for this to be really, really large negative, what I actually want is I want the Kc to be very large. So mathematically then, that coincides with I want to have a very large Kc, a very large equilibrium constant. Because the large equilibrium constant here, this is always going to be a positive number anyways, but the equilibrium constant here is products over reactants. For this value here to become really big, what you end up having here is, I want the fraction to be big, that means I want a lot of products, not a lot of reactants. So we have been seeing already, you can say in the terminology, products are favored, right? Even though we're at equilibrium, even though we would naturally tend to this balance point here, we actually have more products than reactants. If I have a reaction that there's a lot of products, so in this case here we can actually assume reaction goes to completion, the larger this delta G value is, right? What if I had the opposite way? What if I had the delta G where I want actually a big positive delta G? If I have a big positive delta G, well, first thing here, the logarithm term has to end up as a negative, so that negative becomes positive. The way for a logarithm term here to end up in total negative is when the Kc is actually a small Kc. So small positive here, what I want is a small Kc, one that's between 0 and 1. Again, we do this ratio, products over reactants. How is my fraction going to be so tiny? It's when this fraction is tiny, I want very little products, but a lot of reactants. In that case there, we have more reactants. And if you think in terms of just the completeness of reaction, maybe we're proceeding 0% or no reaction, or anywhere in between there. So what's nice about this section here is it gives us a nice connection between the delta G constant that we've been talking about last year with the equilibrium constant expression that we did this year. In Chapter 9, we're going to come back to this once more, and we're going to talk about voltage as well. We're going to see that reactions that have a large positive value will coincide with it being a negative, really large negative delta G, and also a really big equilibrium constant. Right? So hopefully that flushes out a little bit for you for free energy and equilibrium. One other connection I just want to make is, so far we've been studying kinetics, the speeds of reaction, and equilibrium was our second chapter. I want to just tie these two together. Right? So just as an example here, let's take 4 iron as a solid, react with 3 oxygen as a gas. Let's say we've hit equilibrium with 2 Fe2O3 solid, right? So in terms of our kinetics, right, kinetics was talking about the speed of reaction. The forward reaction depends on these guys colliding and going forwards. The Fe2O3 is a reverse reaction, trying to collide, good energy, good geometry, all that's still true. This is actually the rusting reaction. So although the reaction is spontaneous, we know from our kinetics here, nobody wants rust to form, but even though it's spontaneously it's energetically favorable, it doesn't necessarily happen very quickly. If you just take a look at the values, this is actually a heterogeneous equilibrium, so it's a little bit harder for you to actually write out the Kc expression. So let me just quote these values for you here. They actually give us here the delta G of this reaction. They quote it as 1490 times 10 to the 6 joules. Through our negative RT ln K formula that I just mentioned here, we end up getting the Kc value to be some 10 to 261. So this one here, what we can conclude here is, oh, this equilibrium constant is way larger than 1. Definitely products are favored. So we know that the equilibrium lies towards products. And yet, based on our kinetic stuff, it's a very, separately speaking, it's a very slow reaction. Reaction is very slow, given, I would assume, a big EA, a big energy barrier. So totally possible to have a spontaneous reaction. Everything's in favor of it heading forward. The equilibrium constant is humongous. It's much, much larger than 1, but that doesn't necessarily have to mean it actually goes really quickly. So that's one connection we can make. So reaction kinetics has to do with activation energy, the speed of reaction, whereas the equilibrium constants we're looking at are more so when you actually hit equilibrium. Do we end up with more reactions, more products? It could take seconds to reach equilibrium. It could take many minutes to reach equilibrium as well. The one other thing I just want to rehash with you, another connection between kinetics and equilibrium while I have it on the board here. Let's pretend we start off with the reaction again. A and B is going to become C and D. We already had done a little bit of this when we derived the equilibrium expression. So let's have a look at the forward reaction. The forward reaction is going to be some forward constant times A and B. I'm just going to say first order for now. We had done this one here. The reverse reaction depends on the product concentrations. So the reverse reaction, I'm going to say this is K prime, C times D. Remember, we had said by the time that these ones here end up hitting equilibrium, we had set these two being equal to each other. I had pulled these two, when they equal, let's bring the rate constants together. K divided by K prime is equal to C times D all over A times B here. Right. And we had called this one here the equilibrium constant. This is our Kc. Right. Now, we had already made an observation. Well, because these ones here are actually rate constants depend only on temperature. Right? You can think about the Arrhenius equation there. K is AE negative EA over RT. So this rate constant here is only temperature dependent. So therefore, you can poke the equilibrium whatever way you want. You can add concentration, change pressure. You can do whatever you want there. It doesn't change the K, and therefore it doesn't change this K ratio. It doesn't change Kc. We had already been doing this one. Only temperature changes Kc. So the only temperature can change that. It will shift in such a way that this fraction can actually change. What we want to do here is we actually can analyze in a little more detail then. What if we have a situation where, let's say, if my K is a lot larger than K prime, right? In that case, they're looking at this ratio, then therefore Kc will be bigger than 1, right? K was my forward reaction. If my forward rate, if I did this in words for you, if my forward rate is a lot larger than the reverse rate, that one we had said, well, it's like the equilibrium has shifted, or it's going to shift right, and as I shift right, we're going to end up getting more products. What if the reverse? What if the forward rate constant here is actually a lot less than the K prime? So what if the forward rate is actually less than the reverse rate? Well, if I do this ratio here, if the numerator here is as tiny than the denominator, the Kc is actually going to be less than 1, And in that case there, we can actually say more reactants. So even though we've been spending this chapter here mainly looking at equilibrium constant, mainly looking at, does it lie on product side or reactant side, ultimately it does have to do with the fact on the relative sizes of these Ks here. Right? A couple other notes we can make here. Let's say, so again, another if the concentration of reactants increase, this time not because the K increases, but if the concentration, if I increase the A and increase the B, we had said, well, there's more particles that can collide with good energy. That would again imply the forward reaction is faster than the reverse reaction. If the concentration of reactions increase, again, we have a situation where the forward rate is larger than the reverse rate, and therefore we can say shifts right. We can do other shifts. So if I take the product concentration and I decrease the product concentration, right? We had explained this in terms of rate here. At first, the forward rate doesn't care. The forward rate is just A and B. What if I pull down C? Who cares, right? The reverse reaction, the forward reaction is still A and B. As I pull down this one, I have decreased the reverse reaction. Again, I have a situation where forward rate is greater than reverse rate. It's going to end up shifting right. So remember, we had explained this earlier, that the equilibrium doesn't need to have a mind of its own. How does it know to shift right or shift left so that it can replenish, so that they can go against the stress that I have? It basically naturally flows from these rate laws here. The two last factors I want to do with you here is, what if we add a catalyst? If we add a catalyst, we know the answer already. We know that there's actually no shift. Well, what ends up happening here is your equilibrium constant, which is supposedly the forward rate constant divided by your reverse rate constant here. Remember, when you add a catalyst, you provide an alternate mechanism. You get from start to finish. This resting reaction here is, let's say, exothermic here. This is PE against reaction. Basically, our catalyst allows for both rates to actually be a little bit easier, right? Instead of having one uncatalyzed path where the EA is actually very large, uncatalyzed, we end up providing a mechanism that makes it easier for the forward reaction and also easier for the reverse reaction. It's not as high as it needed to be from earlier. So in that case there, because I've actually, if you look more at these rate constants, because I've actually lowered the energy barrier, I've actually made both of these rates here actually equal. So we can say here, both K and K prime are changed by the same ratio, right? Both the forward reaction and the reverse reaction are the same, so therefore there's no overall change to Kc, right? So you made both reactions easier. Most interestingly here, and we'll end off with this one here, is a temperature change. So if let's say temperature is decreased. Just looking at another factor at those Le Chatelier features again. Let's deal with a endothermic reaction. So this time, not adding catalyst or whatever. This time, you definitely have to go over this activation barrier. If I decrease the temperature, let's see if you remember this from earlier. Basically, what's ended up happening, if you look at your Boltzmann distribution, the number of particles, and this is the kinetic energy. As you decrease temperature, the curve actually shifts upwards. So let's say this is my original temperature, this is my T1. As I get to an even colder temperature, all the particles slow down. That is true. So all particles slow down. As all particles slow down, basically they end up stacking up a little bit here, and a lot of them don't have much energy here. Activation barrier was supposed to be the number of particles that had enough energy, the number of particles that actually have higher than this curve. Right, so activation barrier here was just some limit here. And basically the colder graph here, so red is the colder temperature, we have even less particles with enough energy. We have been saying though, let's say this is an endothermic reaction, the EA forward is actually greater than the EA reverse. So even before you cooled it down, the forward reaction was actually harder than the reverse reaction. because the EA forward would have depended on K forwards, the rate constant going forwards, and the other one actually depends on K prime, the ones in reverse. As you cool down the temperature, yes, it may be very well the same temperature difference that you're doing, but if both of these are AE negative EA over RT, because the size of the barriers here were different, the EA reverse here was actually a lot smaller. It was actually a little bit easier to get over. You may have cooled down the temperature by the same degree, but if the activation energy was also lower to begin with, the overall impact on K prime would be different from K, and therefore when we have Kc is supposed to be K over K prime, because both of these rate constants are differently affected by temperature, since the EA forward is not the same as EA reverse, and therefore there will be some overall change to this ratio, and therefore the equilibrium constant will change. Right? So I just wanted to highlight some connections we can make here. You can see if you can draw even more connections on that there. But that finishes off for the equilibrium unit. And then after we finish with our test here, we'll move on into our acid-base chapter. So if you have any questions, let me know. Thanks, guys.